Hello, this is Dr. Gardner. Today we're going to be talking about how to write scientific notation for our numbers in our course. We'll be looking at numbers with very large values or very small values when we write scientific notation many of the times. We'll also be looking at recording measurements and how to record the correct number of significant figures from your measurements when you're using a measuring device. We'll also be considering the significant figures in our numbers and how to keep track of them in calculations. So that's what we're focusing on today. It's very important you master these skills because we need to be able to use these skills whenever we're doing calculations that involve measurements. We also need to be able to convert readily from scientific notation to a standard number and from a standard number back to scientific notation. So make sure you can do these types of problems for our first exam and to help you with your homework. First of all, I would like to look at scientific notation. Let's look at a very large number that we use in chemistry courses that would involve quite a few zeros in our value. So first of all, let's consider if I had 12 grams of carbon. That doesn't sound like a very large mass, but when you consider just how small the size of atoms are when you have carbon atoms, you would have to have a huge number of carbon atoms to add up to that 12 grams. In fact, we'll use a number that's called Avogadro's number in our calculations in the upcoming chapters. And that number is basically a 6 followed by 23 digits before you would consider getting out here to the ones place. So if we consider this value, there's quite a few zeros to write down, and I think you will actually see as we start to learn how to write scientific notation, you're going to save yourself quite a bit of time by not having to write down all of these zeros as placeholders every time you use this number in a calculation. So let's consider how we might write this in scientific notation. Well, first of all, scientific notation indicates an exponent times 10 to a value that determines how many places you might have moved the decimal point from the original number in order to simplify the value. When we write scientific notation, we're going to have a number between 1 and 9 with a decimal point following it, and then any other significant figures we would write after that. So let's say I have 4 significant figures in this number today. If we look at that value, I have 6.022 times 10. After this times 10, we'll notice that we have to a 23rd there. If we consider that we had a number that was much bigger than 6.022, we can understand the scientific notation indicates that to get back to the original standard number that we had, we would have to multiply by 10 23 times. Now, you should all check to make sure that you can see on your calculator where your buttons are for scientific notation. Now, the type of calculator you have will determine how you would enter scientific notation. If you purchase the calculator that I recommended in the syllabus, you will have an EE function on your calculator. That EE function will provide this times 10. You just need to type in to the 23rd. So I would type into my calculator 6.022, then hit my EE button if I had the calculator I recommended for the course, and just type in 23. That would indicate that I had this value in scientific notation to the 23rd power. Now, some other calculators may have the EE notation for scientific notation as a secondary function. Some others may have you enter that via other methods, so I recommend looking at your owner's manual tonight for your calculator and determining how to correctly enter scientific notation in your calculator. If you are unable to use scientific notation with your calculator, you're going to find that you're going to have errors in your calculations, so be very careful about that. Okay, so let's see how I could generate this value, 6.022 times 10 to the 23rd, when I look at the original number for the number of atoms I would have in 12 grams of carbon. Well, first of all, if I imagine that it's not shown here, but if I imagine that the decimal point is where I have our laser pointer right now, if I were to move that decimal point to the left, now I'm moving it to the left to make this a smaller number that would be easier to write with fewer zeros. So if I move it to the left, I could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 digits. If I moved the decimal point until I had a number before it that was between 1 and 9, which is our 6th value here, I would have had to move the decimal point to the left 23 times. Now, when I write a standard number in scientific notation, whenever I move the decimal point from the right to the left to get a smaller value, we get a positive exponent, so a positive 23. Now, if I wanted to convert this value back to the original standard number, my scientific notation value, I would move the decimal point back to the right 23 times to regenerate 6.02200 with all my values out there by moving my decimal point out to the 23rd place. So you will have to be able to, on tests, convert standard numbers, such as the one shown here, to scientific notation with the correct exponent. You must also be able to convert values in scientific notation back to standard numbers. Just remember, when I move the decimal point to the left, we end up with a value that has a positive exponent. And to convert that scientific notation value back to the standard number, I would have to move the decimal point back to the right 23 times in order to generate the original number. Okay. Whenever you see these positive values for the exponents, just realize that you have values that are going to be greater than 10 that we're looking at. So in this case, the larger the exponent is when it's positive, the bigger your value would be. Okay, so this is a very large value that I see in this case. It would take this many atoms of carbon, because they're such small particles with such small masses, in order to add up to a whole 12 grams. Useful to know this is how many atoms of carbon and 12 grams of carbon, because you can go into the lab and measure out 12 grams. Now let's consider something that's very small in mass. So if I have a single carbon atom and I want to know its mass in grams, that's going to be a very tiny value. So I could write that as a standard number, but do you see all of these zeros I would have to write out? There's going to give me many opportunities if I keep using this in calculations and I have to write it several times. I'm going to have many opportunities where I'm going to forget to write down one of these zeros and have my decimal point off. That would increase my chances for error when I'm looking at these types of numbers and calculations. So when I have a very tiny number, just like when we had a very large number in the last example, it's helpful to put it in scientific notation to have a more manageable value that we can work with. So here, I would move the decimal point, instead of going to the left like we did in the previous example, we would move it to the right, and I'd have to move it to the right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I'd have to move it to the right 23 times. Now, if you forgot when you wrote the scientific notation to write a negative 23, if you forgot to put that negative sign, if you had put a positive 23, we'd think this was a huge mass. That would be much more massive than we would expect to have for any individual atom. Be much more massive than we expect for most objects you would interact with. Okay, so I need to have that negative sign. So remember, when you have a negative exponent in your scientific notation, it indicates you had moved for a very small value, the decimal point, to the right until I had a number that was non-zero and a value between 1 and 9. Okay, so I end up with the value here of 1.99 times 10 to the negative 23 grams. Again, I would not have moved the decimal point to the right again, because if I were to do so, I would have ended up with a value that was greater than 1 to 9. I'd end up with 19.9, not proper scientific notation. I just want a value between 1 and 9 before that decimal point. Now, if I were to read this value in scientific notation and want to convert it back to a standard number, since I have a negative 23, that reminds me, that negative exponent, that I have a very small value, I'd want to move my decimal point back to the left 23 times to get back to the standard number. So I'd move that decimal point to the left 23 times until I generated the original mass in grams of a single carbon atom. So be sure that you practice going back and forth with these values with the homework, and please ask for help if you need any help from your instructor. Okay, so we've looked at a couple of values in scientific notation. We looked at the value for the number of atoms in 12 grams of carbon. That was a very large value, so I have a positive value, exponent in the scientific notation. If I have a very small value, like the mass in grams of a single carbon atom, well, when I put that in scientific notation, I should see a negative value. You should be very careful to have the correct sign on your exponent in the scientific notation, because if I forget and put the wrong sign down, the meaning changes dramatically. A positive 23 is a huge number. A negative 23 is a minuscule small number. So we want to make sure we have the correct sign there. Now, the reason we're really using the scientific notation, I said before, we'd likely forget to write down some of these zeros if I was writing these numbers down several times in the course of a calculation. So we could say that the scientific notation is more compact. Okay, we're only going to indicate the number of significant figures in our value, as we'll be seeing today, as the n value here in the scientific notation. That n value is going to be between 1 and 9 before I hit a decimal point, and then any other value that's significant that I need to write down will be after the decimal point. So for example, I can have 1.99 0.99. That n value before the decimal point, though, is between 1 and 9. Okay, my exponent here in red, that n value, that's either going to be a positive or negative whole number integer that indicates how many places I moved the decimal point. If I get a negative 23, it means from the original standard number I moved the decimal point to the right 23 times. It was a very small value to begin with, so I'd write that negative 23 for the n value. If I have a value that's very large, I'd have to move the decimal point from the standard number here shown first. I'd have to move that to the left 23 times in order to generate a number in scientific notation, and so my n value would be quite large. Okay, so be sure you can write numbers in scientific notation. Keep practicing on your homework to be able to do this. Now let's look at a couple of values and actually convert them to scientific notation together. So we don't always have to have such huge numbers or such small numbers. We can have some intermediate sized numbers that we can practice with to begin with. Let's consider we have the number 568.762. This is not in proper scientific notation as written because the decimal point would need to be to the left 2 locations in order to have a value that's between 1 and 9 before the decimal point on the left hand side. Right now there's a value that's 568, much larger than our maximum of 9 that we set to the left of the decimal point. So since this value is larger than 0, in order to convert it to scientific notation, when we get these larger values, I need to move the decimal point to the left twice. Okay, so if I move that decimal point to the left twice, we're going to end up having proper scientific notation written as 5.68762. So I have a value before the decimal point between 1 and 9. It's a 5 in this place. Since I moved the decimal point to the left, though, I have to indicate how many times I moved it, or somebody reading this number wouldn't understand how large it originally was. So I need to put times 10, and then how many times I would have to multiply this value by 10 in order to generate my original number. So I'd have to multiply by 10 2 times. So I put an exponent here to the right of a 2. The decimal point had been moved to the left twice in order to generate this value. Values that are larger than 10 will have positive values here. Values that are smaller than 1 would have negative values for these exponents. So this is a large number, so I need a positive exponent. Let's consider if I have a smaller value. So let's say we have this value, 0.000007. In order to put that in scientific notation, we would need to move the decimal point to the right. So I count this. This is like when you're looking at different songs you might have seen as a kid where they have the bouncing ball looking at the words, right? Here we have a bouncing decimal point as we move this to convert it to scientific notation. So I will go ahead and follow that decimal point. I need to move it to the right until I get a non-zero digit and a value that's between 1 and 9 before the decimal point. So I'm going to move to the right 1, 2, 3, 4, 5, 6 times to the right. So I get an exponent that's going to be a 6 here, but since I moved to the right because it was a very small number, we need to put a negative 6 for my exponent. So I'd rewrite this number as 7.72 times 10 to the negative 6. I had to move that decimal point to the right 6 times in order to generate this value. The negative value tells me that in order to produce the original small number again, I would have to divide by 10 6 times in order to get the original number. If I forget to write that negative sign, it changes the meaning dramatically. If I had written a positive 6 here on accident, that would indicate that you thought we had to multiply by 10 6 times to get a much larger value. So the sign is very critical that you write the right notation on the sign here as a negative for small values or positive for very large values before I converted them to scientific notation. Okay, so as a class, let's try this one. So if you'd like to, go ahead and pause the video and let's try to answer this question. Recently, I read that the U.S. federal deficit was about 17.8000000. So if you think about that, that's going to be in the trillions. So I have 17,800,000,000,000, right? And then this changes so much beyond that hundreds of billions that I didn't bother measuring any more closely because it just changes so quickly. Okay, so as we look at this value, I want to put it in scientific notation. Okay, so this would be a perfect time to pause the video and try to put this in proper scientific notation. And everybody should try to pick the correct letter for the answer here. Okay, so try to convert it to scientific notation. Okay, now that you've tried to convert this to scientific notation, we have to realize it's a very large value. So right away, that should tell me I should get a positive exponent. So if I'm thinking about that, I know that the answers A and B cannot be correct. A very large number like the federal deficit in scientific notation would have a positive value. A negative value would indicate that our federal deficit value is much less than a single penny. I mean, we would really like it if that were true, but it isn't. So A and B are incorrect just by understanding the signs on your scientific notation. Now, E may have been correct for you, but I won't actually give credit on a test if you just say you don't have a clue. So you actually would have had to pick another choice, even if you thought E was quite true in your situation. So I'm going to have to choose between C and D. Now, if I look at C and D, only one of these is improper scientific notation. Remember, proper scientific notation has a value that's to the left of the decimal point between 1 and 9. Okay, so choice D, just by glancing at these two choices, I could have determined that choice D is the best choice. It's in proper scientific notation. Now, we can read choice C with respect to 17.8 times 10 to the 12th, but it's not in strictly proper scientific notation. This type of notation is actually kind of a intermediate notation that isn't strict scientific notation. The value's greater than 9 to the left of the decimal point. If I want to convert this to proper scientific notation, I'd move the decimal point one more place to the left, which would increase the exponent from a 12 to a 13. I end up with D as my answer. So even though I can read C, I understand what it means. It's not proper scientific notation, so D would have been the best choice here. Now, to make sure you understand where I'm getting the value of 13 here, let's consider where we would have had our decimal point in the original number. So my decimal point, even though it's not shown, would be after the last zero to the right, since I hadn't shown a decimal point. So if I consider my decimal point being where I have the laser pointer right now, to convert this to scientific notation, I'd move to the left until I had one digit between 1 and 9 to the left still. And since I'm moving it to the left, I get a positive exponent on my scientific notation. So let's go ahead and do that. So I count it, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places to the left. I would have to move my decimal point in order to put it in scientific notation. And so I'd write it as 1.78 times 10 to the 13th dollars for the federal deficit. Okay, that's a pretty big number, but now we know how to convert it to scientific notation, and we can write it much more readily in this form. Okay, so kind of keep that in mind. Now, what you might want to do is try to practice converting a few numbers into and out of scientific notation with your instructors. If you want to, you can email me and ask me additional questions. Now, we're going to look at the metric system very briefly next, but realize we're going to spend an entire lecture looking at the metric system and how to do conversions with the metric system coming up next. So I'm going to give you a very brief preview of the metric system. First of all, if we consider having some standard units for the metric system that were developed by the French in order to have a more systematic method of taking measurements than had been developed by the English, who were dealing with length measurements, for example, in inches and feet and yards and miles, and the values relating the two was different in every case, right? That made it kind of confusing, whereas the French developed a committee, and they spent quite a few years trying to decide on the best system of keeping track of measurements, and they decided to relate different magnitudes of measurements using prefixes. And they said the difference between these prefixes would all be in the metric system that they had developed by factors of 10. So it would be much easier to remember the relationships as long as you knew the prefixes. Much easier actually than having to remember that there's 12 inches in a foot, and that there's 3 feet in a yard, and there's 5,280 feet in a mile. Trying to remember all of these different values for the relationship between the different English systems is actually quite a bit more challenging once you learn the metric system. So let's consider if we have a base unit. Now, our base units for the International Standard Units of Measurement for the metric system are usually for length, meters. For mass would be grams. Okay, for time would be seconds. Okay, for volume would be liters. Okay, we'll be looking at this in greater detail when we cover the metric system, but let's just compare these. Where I have the two dashes on this table, that would be my base unit, whether that's seconds, meters, or liters, whatever my base unit was, I could go ahead and have that here. However, if I change by factors of 10, the relationship of the base unit to other prefixes, well, then I can use, for example, if I have let's say, a meter here for my base unit, well, 1 meter, I don't use any prefixes. I just use a lowercase m. However, if I want to look at a kilometer, a kilometer, we're going to have a lowercase k to indicate as a symbol for kilo. Now, the prefix kilo just means I have 1,000 times the base unit. Okay, so if I have 1 kilometer, that would be 1,000 meters. Okay, or if I put that in scientific notation, that would be 1 times 10 to the third meters. Or let's say I had a megameter. Well, we use a capital M for a megameter, so I don't confuse it with the lowercase m used for a millimeter. Well, a megameter, that capital N means I have 1,000,000 of the base unit. So if I'm talking about meters as my base unit, a megameter would be 1,000,000 meters. Or if I put that in scientific notation, 1 times 10 to the 6th meters. Okay. Now this works for small values as well. So let's consider if I have a centimeter. It's really easy to remember what a centa means as a prefix, because how many cents are there in a US dollar? Okay, hopefully you remember there's 100 cents in a dollar, or I'm a little concerned. Okay, so if you can remember there's 100 cents in a dollar, you know that centa means that you have 1/100th of the base unit. So I would have to have 100 centimeters, since each one is 1/100th of a meter, to add up to an entire meter. So if I have a centimeter, that's 0.01 meters. It's 1/100th of a meter. If I put that in scientific notation, I'd move the decimal point 2 places to the right. I'd have 1 times 10 to the negative 2 meters. Okay, so that's 100th of a meter. If we went to a micrometer, well, that's 1,000,000th of a meter. So it would take 1,000,000 micrometers to add up to 1 meter. Now we use the Greek prefix, the Greek letter mu as the prefix for micro. So I use the Greek letter mu here before meter to be micrometers. If I had micrometers, like I said, I'd have to have 1,000,000 of those to add up to 1 meter. If I had just 1 micrometer, well, that would be 1,000,000th of a meter, so 0.000001 meters. Now, as we start to see very small values or very large values on the metric system, you can see where it's useful to write these in scientific notation. So if I were to write this in scientific notation, I can move the decimal point to the right 6 times in order to have a value that had a number between 1 and 9 before the decimal point. If I convert that to scientific notation, we'd write it as 1 times 10 to the negative 6. So that would be how many micrometers I have. Okay, now if I were to continue going to smaller values, I could have a nanometer. Now a nanoliter or a nanometer or a nanosecond, those are all 1,000,000th of the base unit. So if I had a nanosecond, that would be 1/1000th of a second, a very short frame of time. If I have a nanometer, that's 1/1000th of a meter, a very short length. Okay, so here I have nanometers, let's say. If I had 1 nanometer, that would be 1/1000th of a meter. Now I can write that out with all my zeros, or I can put it in scientific notation and say that 1 nanometer is equal to 1 times 10 to the negative 9th meters. Again, when we see these negatives in the scientific notation, we had very small numbers to begin with. If I want to convert back out of the scientific notation, well, I would have to move the decimal point to the left 9 times in order to convert it back to a standard number. So you need to become familiar with these. So right away you want to start memorizing what the meaning of the metric system prefixes are. Now hopefully your math classes have already been working with the metric system previous to this course. If they have not, you'll have to put extra time into learning the metric system, and you might want to ask me for some additional help, or the instructor at your location, you might have to ask them for some additional help to learn the metric system prefixes. But you need to start practicing these as soon as possible before an exam. Now, even though we've been using these Greek prefixes, I'd like you to know another unit for length. Okay, so I'm going to talk about an angstrom. 1 angstrom is actually 1/10th of a nanometer, so it's an order of 10 smaller. So I move the decimal point. I would have to move it again 1 additional point to the right in order to convert it to scientific notation. So that would be 1 times 10 to the negative 10 meters. Why I like you to know what an angstrom is in a chemistry course is because when you start dealing with small atoms or small molecules, the dimensions we look at can be on the order of basically angstroms in size. If you get up to nanometers in size, you're starting to approximate sizes of small biological molecules. For example, if you start looking at strands of DNA, well, if you look at a single or a double-stranded DNA, you start to get in the nanometer ranges for sizes roughly. Okay, if I'm talking about water molecules or a single atom, we're closer to angstroms in sizes. So it's really useful to know that 1 angstrom is equal to 1 times 10 to the negative 10th meters. Now note we aren't using the prefixes like all of the others. other metric system prefixes, so it is a unique length measurement. I love to throw angstroms or a variety of the prefixes from the metric system onto our tests, especially for exam 1 when we're doing unit conversions. So make sure you know all of these. I'll pick a variety. I'll make sure you know the difference between a lowercase m for milli for 1,000th of a base unit. I'll make sure you know that it's different than a capital M for a mega, which is a millionth of the base unit. So make sure you know those. Another common mistake that I see students perform is when we talk about deci, well, a lowercase d is a tenth of the base unit. So a decimeter is 1/10 of a meter. So I'd have 10 decimeters have to be used to add up to a whole meter. Whereas if I had a decameter, we either use a capital D for deca, or sometimes we use a lowercase dA for deca. That's going to be 10 of the base units. So if I have 10 meters, that would be 1 decameter. Just be careful because sometimes we'll use a capital D for deca as well. So if you start seeing capitalized prefixes in some of these cases, you're thinking that's a prefix that indicates a large number of the base unit. If we see lowercase prefixes for our abbreviation, it will often, but not always, but often it will indicate smaller values than the base unit. So kind of know that's the deca, centa, milli, micro, nano, pico, and femto types of units. Okay, so let's do another class problem. So at any point here, you're welcome to pause this little quiz question and then try to answer this and then compare your answer to what is correct. So we want to convert a very small number here, the size of a water molecule in meters. We want to convert this to scientific notation. So go ahead and pause that and try this. Okay, so if I look at this value being very small, just from your understanding of writing values in scientific notation, a very small number should actually have a negative exponent in the scientific notation. So the best choices here immediately would be B or D. E might be correct, but it's not going to get you credit. So if you decide you don't have a clue about what to do here, that's not okay. You need to kind of be practicing this. Now, I know since this value is very small, I wouldn't pick a very large scientific notation, that would be like the positive 10 here or the positive 12. So I can immediately exclude those from my choices. I don't have A or C as my choice. So my answer should be a B or a D. Again, if you recognize that B is in the best proper scientific notation with one digit between 1 and 9 to the left of the decimal point, you might have picked that one. But let's make sure you understand how to convert that to proper scientific notation from the original number. Now my decimal point is shown here to the left. To put it in proper scientific notation, I need to move it to the right until I have one non-zero digit to the left that's between 1 and 9. So that's going to be my 2. So I'm going to move my decimal point here to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So that gives me a value that's to the negative 10th in scientific notation. So if I write 2.78 times 10 to the negative 10th meters for my scientific notation, that would be the size of a water molecule. Well, if I'm looking at that, that means that to convert this scientific notation number back to a standard number, I'd have to divide by 10 times when I see that negative exponent. Okay, if you had accidentally picked A, that would have been a much bigger value, because to convert that back to a proper number, a standard number, we would go ahead and multiply by 10 times. Okay, that would be a very huge value. That's much bigger than any water molecule has ever been, obviously. It's much bigger than the common objects that you interact with, and very unreasonable. So your standard water molecule, depending on the dimensions that you're measuring of the molecule, is about 2.78 times 10 to the negative 10th. Now I want you to think about how this relates to nanometers. What was our size in nanometers? Okay, so if I had 1 nanometer, what is that size with respect to a standard meter? Hopefully you remember that 1 nanometer is equal to 1 billionth of a meter. Okay, so that's 1 times 10 to the negative 9th meters. Okay, so if I have 1 nanometer, that's 1 times 10 to the negative 9th meters. Well, that's going to relate to my size of the water molecule. My water molecule sizes here was to the negative 10th. So if I were to convert that to nanometers, we can tell that I would have had a much larger value here. So to the look at nanometers, we have a smaller value. I misspoke. We have a value in nanometers that's going to be moved the decimal point to the left once. It's not a proper scientific notation, but that would convert this to a -9th meters. So what I'm seeing is I have less than a third of a nanometer is the size of a water molecule. And that's not surprising because I already told you once you start to look at a double helix of DNA that the dimensions of that are in the order of nanometers, which is much larger for the diameter of that double-stranded DNA than a single water molecule. Now, however, if I wanted to relate this to angstroms, remember angstroms are going to be 1/10 of a nanometer. So your nanometers were a billionth of a meter, well, your angstrom is going to be 1/10 of that billionth. So it's 1 times 10 to the -10th meters is 1 angstrom. So if I start to look at these, my value for B of 2.78 times 10 to the -10, well, that's the right scientific notation to relate to angstroms readily. So I could say that a water molecule, the dimensions here are 2.78 angstroms. Okay, so it's very helpful to know some of these prefixes and be able to relate them to small molecules or atoms in a chemistry course. Okay, so if I have scientific notation, I want to keep track of it in calculations. So say I want to add or subtract my scientific notation. Well, I need to realize that when I add or subtract scientific notation, well, my value for the two values that I'm looking at when I'm adding or subtracting, I would like to convert those to the same exponent. Okay, so as long as I have the exponent n to the same value, I can just add or subtract the two numbers here in blue. So if I look at 4.31 times 10 to the fourth and 3.9 times 10 to the third, I can't yet add or subtract these just by adding or subtracting the value in blue because their exponent in the scientific notation is different. This is to the fourth power in the scientific notation, and this is to the third. In order to just go ahead and add or subtract the number in blue, I need to match these two exponents. So I could, for example, try to convert 3.9 times 10 to the third to a value to the fourth power. Okay, now if I'm going to convert something to the fourth power, I need to move the decimal point to the left one place. So if I move the decimal point to the left, what I'm going to see is that my exponent for each place I moved it increases by 1. So let's move the decimal point to the left once. It will no longer be in proper scientific notation, but we'll see that we end up with having the same exponent on the two values. So I have 4.31 times 10 to the fourth and 0.39 times 10 to the fourth. The nice thing about it is if you have your two values to the same exponent, you can go ahead and add the values in blue and you maintain the original exponent. So we go ahead and do that. We add 4.31 to 0.39. We end up with 4.70. The exponent's maintained as 10 to the fourth. So there's a really quick technique when you're doing this by hand. And some of the questions that we generate, you might find that have very large exponents. Some of your calculators will have difficulty in determining their values. So if you're having trouble with large exponents with your calculator, you might need to do a quick calculation by hand like we're seeing here. Now let's consider if we're multiplying exponents. If we're multiplying exponents, let's say we have 4.0 times 10 to the -5 times 7.0 times 10 to the third. You don't have to convert these exponents to the same value. You can just go ahead and multiply your number in blue here, 4.0 times 7.0. Okay, and then you can add your exponents when you're doing this. Okay, so as I do this, I take the 4.0 times 7.0, and then I just add my exponents. Remember, if I have a negative exponent, we're going to take a -5 plus 3 to find out my new exponent. So I write my new value. It's 4 times 7 is 28, and then I have 10 to the -2 for my exponent. Now, this isn't proper scientific notation, so we're not quite done. If I want to put it in proper scientific notation, I'll need to move the decimal point one place to the left, so I get 2.8. But if I move it to the left, I must increase my exponent value by 1. Since this is a -2, increasing that by 1 would give me a -1. So my proper scientific notation is 2.8 times 10 to the -1. So this would be the best answer in proper scientific notation right here. So just remember, when you're multiplying, just add your exponents and multiply the numbers in front. Very simple to do so. If you're dividing your values, well, what you can do is take your number in blue here, that's before the scientific notation, you can just divide them. So if I take 8.5 times 10 to the fourth divided by 5.0 times 10 to the ninth, I can merely take 8.5, divide it by 5.0, but that doesn't tell me what to do with the scientific notation exponents. In this case, whatever number I'm dividing by in the scientific notation, I'm going to go ahead and subtract that exponent. So I'm going to take 4, subtract 9, And so I would write that as taking 8.5 divided by 5 for my values in blue before the scientific notation. I take 4 and subtract the 9. Okay, so I'd get a new value that's 1.7 times 10 to the negative fifth. It's in proper scientific notation, so we're okay with it. Now, a common mistake that I see that students perform is if one of these exponents to begin with was a negative, well, let's say I had a negative 9, a very small value from my 5.0, if it was 5.0 times 10 to the negative 9, and I were to subtract it, I'd be subtracting a negative value, so you end up with a positive for the second number here. So be careful. If you divide by a small exponent value that's negative, you're going to be subtracting that negative value. You get a positive again, so be very careful with that. Okay. So we've looked at how to write scientific notation. We've had a very brief preview of the metric system, which we'll look into much greater detail later. But now that we've considered this, we want to look at measured values. When we're considering measured values, we need to be able to keep track of the meaning of the values that we've written down that have been measured and how many digits are meaningful. Unfortunately, not every measuring device was made equally. Okay, so let's consider significant figures. Now, sometimes significant figures are called significant digits, or sometimes we'll abbreviate significant figures as sig figs when we talk about them, but just realize we're talking about how many digits were measured that have meaning. So we're going to be looking at how to do that. So first of all, I might have some measured values out there that can be measured, let's say, as 3 centimeters. So if I write down in my notes, in my homework notebook, or in my lab notebook that I have 3 centimeters, well then I know 3 centimeters would be indicated as being measured to the ones place. So as I measure my 3 centimeters to that ones place, we're going to find that only 1 digit was measured, only 1 digit was significant. Now, if I have a more careful measuring device that measures out to, let's say, the tenths of a centimeters, I could have 3.0 centimeters. There's 2 significant figures here. If we measure out to the hundredths place, I could have, as we see, better and better measuring devices with finer divisions on the scale for length. We can see here we'd have 3.00 centimeters. We'd say there's 3 significant figures. It indicates that I measured all the way out to the hundredths place here. So what's happening is we're having increasing precision, meaning our measuring devices have finer and finer scales that we're using. And I'll show you an example of this with respect to using a ruler here in a moment. Now, if I had an additional measuring place on my measuring device, I could go out maybe to the thousands places, so I could have 3.000 centimeters, so my thousandths place would be the correct number of significant figures. Now in the laboratory, when you're performing measurements, you need to write down the proper number of significant figures in your notation. If you have the wrong number of significant figures compared to the measuring device you use, you might be throwing away some significant figures. Or if you're doing a calculation in your calculator from those measured values and you round to too few significant figures, you're throwing away useful information. So you want to make sure in all of these cases that you write the proper number of significant figures with respect to the measuring device you used. Okay, so be cautious with that. So as we're looking at these different circumstances, let's actually consider when I'm taking a reading off of a measuring device. So let's say that we have significant figures that we're going to be writing down for a measuring device, and realize every measuring device that you use that has basically individual divisions on it. This would be like in your graduated cylinder or on a meter stick or on a set of calipers. When we're looking at the divisions on there, well, we're going to go ahead and record several digits in the measurement plus 1 estimated digit. So we estimate 1 place beyond the divisions with respect to whatever measuring device we have. So let's pretend we have 2 different types of rulers in our lab, and let's see how we write the proper number of significant figures with those 2 different rulers. So first of all, let's consider I have a ruler that just has marks for every centimeter. Okay, now this ruler would be less precise than most rulers that you have in your laboratory that might be measuring out into individual millimeters. But let's say this is the best ruler I have handy at the time, only centimeter marks, and let's say I took a nice blue paper clip here and I wanted to measure the number of centimeters in my measurement here. Okay, so I put one end of the paper clip, if I'm looking for the longest dimensions here, the length, at the 0, and then I go ahead and take a reading out here to the other end of the paper clip, and if we're looking at the paper clip's length, and I want that in centimeters here, we notice that we're greater than 1, greater than 2, greater than 3 centimeters, so I'm measuring out that it's greater than 3 centimeters. Now that's as far as I can measure with the divisions, but remember I said the last digit that we write down, the last significant figure we write down is actually going to be an estimated value. So if I have my my divisions here between 3 and 4, and I have a value in between those. I mentally divide between those two marks by 10. So I think, okay, how many places of 10 would we have there? So I want you to quickly write down what you think this is. What's my value in centimeters? Remember, the last digit that's going to be out to the tenths place is going to be my value that I've estimated. But it's still a significant figure. There's still some meaning to that here, but I can't estimate any further than that. Okay, so I might write down that I have my length here as 3 centimeters, but we should estimate one more digit beyond the markings. So I would go ahead in red and make an estimate. I'd say maybe it's 3 1/3 centimeters. So I'm estimating it's 3.3. And to record a proper number in my notebook or whenever I'm taking measurements, I need to show units. So if I had just written this answer as 3.3, I might get a point deducted on a test or in my notebook because I haven't written down what the units were to that value. If you don't write that down and somebody reads this as a length measurement, they're not sure if you have this in meters or decimeters or centimeters or millimeters or micrometers or nanometers unless you write that unit. So I need to write the unit down as well. So this last digit, though, was estimated. Now, some of you may have disagreed with me. Did any of you think this was 3.2 centimeters or 3.4 centimeters? Those values are also equally correct, because we estimated that last digit. So we have some uncertainty in the last digit that we estimated. Now, however, I wouldn't write down any more digits as significant, because if you go beyond that last estimated digit, well, we have error that's going to be probably several numbers in that estimated digit here, depending on the measuring device. I might say here that I have plus or minus half a centimeter for my error sometimes. So it doesn't really make any sense to measure out to the hundredths place when the tenths place was estimated. So I wouldn't want to record any more digits. So 3.3 centimeters. The only time you might want more digits is if you have a more precise measuring device. So should we look at a more precise ruler and see how that would change our value in significant figures? Okay, so this value we just measured had one measured value, one estimated digit. So there's always just one estimated digit. I don't go beyond that. There's 2 significant figures, though. So all the measured digits and that one estimated digit add up to all of your significant figures. So let's go ahead and look at one more ruler. So here's a ruler that probably looks closer to the ones you'll run into in the laboratory more frequently or in your homes. When you look at the centimeter side of your ruler, you'll notice that there should be millimeter marks. Now remember, your millimeters are going to be thousandths of a meter, and your centimeters are hundredths of a meter. But it takes 10 millimeters to add up to a centimeter. So I can go ahead and count the divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so there's 10 marks between the centimeter marks. That's going to be millimeters in size. So let's go ahead, though, and record our value for the length of the paperclip again, but use this more precise measuring device. Hopefully you already recognize we're going to have more significant figures now that we have finer divisions. Okay, so I'm going to go ahead and write down my measured digits. Now I measure out to 3 centimeters, but I have finer divisions here, so I can go further than that. So I'm going to say, well, I'm 3.1, 3.2, not quite to 3.3, so I'm going to write 3.2 for my measured digits. I would have had to be at the 3 mark or beyond to write 3.3, okay, but I can estimate between the lines. So between my lines here that are much smaller, tenths of a centimeter or millimeters, I can estimate by mentally thinking about 10 divisions. So I'm thinking here, well, this looks like it's close to maybe 3.28. So my last estimated digit is my last significant figure. There's some uncertainty there. Some of you might have said 3.27 or 3.26, or some of you might have said 3.29. Okay, so if you were off by a couple of places in that estimated value, we still consider them just as valid because there's a little bit of uncertainty in that last significant figure. Now, there'd be too much uncertainty if we went beyond millimeters with the markings on here for there to be any meaning, so I wouldn't write any more digits down as being significant. Okay, now I should always write my units down. If I count my significant figures here, I need to recognize in green are 2 measured significant figures. The last significant figure will always be an estimated value when we're taking our readings like this. So I have 3 significant figures, 2 measured and 1 estimated. We will only ever see 1 estimated significant figure, though. Okay. Now, we know there's a little bit of error in this last significant figure in red. Okay, unless you're told otherwise, it's a pretty safe bet to assume there's about a plus or minus a about half of that place. So if I have my lines at millimeters, I could say that I have plus or minus in that last estimated digit here of about 5, depending on the person reading it. So we might say, well, plus or minus 0.5 millimeters. So a wooden meter sticks, the tolerance, the precisional error that we'd be looking at in that last estimated digit is going to be about half of a millimeter. Okay. Now you won't always be in a chemistry lab using rulers. We will for some of our labs in here, but sometimes you'll use glassware. So let's say we're taking a measurement in the lab with our glassware, and we are using a graduated cylinder. And so here's my graduated cylinder. I've blown this up so it's a little bit larger so I can see it better. And we notice that there's a line at the 40 mil mark. That's this long line here, and the 50 mil mark. I have water content in my graduated cylinder that I want to take a reading for. Now, unfortunately, when I read the level of the water, it's not flat. We actually end up with some attraction between the water molecules to the silicon oxide glass surface of the graduated cylinder. That attraction causes some capillary action on the sides to draw water up on the sides due to the attraction. So we're going to see in that case that we see some curvature where the edges of your water go up slightly. So we call this a meniscus when we see that curvature. For water, the meniscus will curve down, and we take the reading at the bottom of the meniscus. So I would take the reading right here at the bottom of that curvature. Now be careful, because other liquids don't always curve down with their meniscus. So we might say that's what's wrong with the statement on this picture where it says always read the bottom of the meniscus. True with water, but let's say I had something like mercury. Liquid mercury has much stronger attractions, metallic attractions between with metal bonding between the mercury atoms and their attraction of the glass, so it actually beads up and it curves upward in the center. So sometimes it's better to say let's measure the middle of the meniscus, whatever's happening there. Here with water, the middle of the meniscus is curving down, so I read the bottom of the meniscus. For liquid mercury, let's say in a mercury barometer, I would read the top of a meniscus for my barometer. Okay. Now I want to make sure my eye is at the same height as this bottom of the meniscus, so I want to avoid what we call parallax error. That's your error due to the position of your eye when taking a reading. So if my eye were above the level of the graduated cylinder's water level or below, I'm going to actually take a reading that's off slightly. If I'm right at the same height, then I'm going to get a good reading. Now, many of you may not have steady enough hands to hold the graduated cylinder to take this reading, so I recommend just putting it on a very secure surface that's steady with few vibrations, like maybe a lab bench, and then I would squat down slightly and get my eye at this height to get the best reading. Okay, so that avoids that parallax error due to the position of my eye. So when I take a reading here, I need to look at my graduated cylinder. So here I have 40 mils, and let's look at how many divisions were the 50 mil mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 1 mil divisions between the 40 mil and the 50 mil mark. So I know when I record this, I could record this as 44 milliliters. Now 44 milliliters would be all of my measured significant figures. But I should have one last digit that's estimated when I write a value down that's been measured. So that last estimated digit would be mentally dividing between the milliliter lines by 10. And so you might say that this is 44.5 or 44.4 or 44.6. There are some likely values you might have picked here. Those are all equally correct because there's a little uncertainty in that last estimated digit, but I definitely wouldn't estimate any further. Most common error I see students perform in lab is that they will stop writing all of the significant figures at just the lines, and they won't write their estimated value down. Now, I'd hope that all of our lab instructors will remove a point every time you're throwing away a significant figure. So if you're not writing down your estimated digit on significant figures, you shouldn't get complete credit for that value because you're throwing away meaningful information. We weren't exactly at 44 mils. We weren't exactly at 45 mils. We were in between. So 44.5 with that estimated digit gives me more information than if I had rounded at this point. So I don't want to round yet. Now, a lot of glassware will have unique tolerances with the divisions. A 10 milliliter graduated cylinder, for example, if it's class A, which is one of the higher quality graduated cylinders, has a tolerance that we would say the reading on it, because the divisions are a tenth of a millimeter, are about 5/100ths of a milliliter for the error for that last estimated digit. Whereas if I have a 50 milliliter graduate cylinder, well, the divisions would be half millimeters, and the error for the estimated digit would be about a quarter of a milliliter. Okay, now 100 milliliter graduated cylinder, that looks like maybe the graduated cylinder we just looked at, right? There's going to be 1 milliliter marks, okay, and we end up with having divisions that are going to be 0.40 milliliters with respect to that. And so as we're looking at those divisions, we can realize that that's going to have larger error as our spacing between the divisions are larger. So we end up with 0.4, so 4/10 of a milliliter for the error for that 100 milliliters. So the size of your glassware, how fine the divisions are, as well as the tolerance for specific glassware on the grade of it's going to be important. Don't worry too much about grading glassware right now, but it's something to be aware of, that different glassware is not always equal quality for the precision of the measurements you can take with it. Okay, so we're going to pause there for today, and next time we're going to be looking at precision and accuracy in the laboratory when we're considering significant figures. Okay, thank you very much.